Session 9, presented by Antonio Bianconi, and the title is Complexity and Spin-Object Coupling Favoring ITC Superconductivity in Nature and Artificial Heterostructures. Please start.
Okay. I am very pleased to speak at the International Conference ICM 2023 in Austerlitz. I'm not sorry to be in presence and to see all my friends there. That is a very important event in the field of superconductivity in this year. I will speak about the advance in the last 35 years on the understanding ITC superconductivity, and we think we have made some breakthrough in the field. The idea is manipulating a spin-orbit coupling in superlattices of quantum wells. So it's a case of fundamental physics. My talk is dedicated to Alex Muller, that passed away in January this year and left a big empty space in our community. Alex was an heretic and revolutionary scientist, which was focusing his search of high temperature superconductivity and the old dream of quantum physics to the open perovskites. Alex Muller was a student of Pauli, and he knew quantum mechanics very well and was very experimentalist, using techniques like electron paramagnetic resonance and Bose-Bauer to study local structures. So he was not coming from the band structure community. He was not coming from superconductivity community of BCS theory. He was completely ready, looking for localized states and condensation of bosons, polarons. So the idea was to focus on lanthanum-2 copper-4, which is a copper-2 plus compound, and to make a mixed valence system with copper-2 plus and copper-3 plus using dopants. Alex was successful, and the discovery was so important that you can see in the drop that change in the field of ITC superconductivity, that now we reach room temperature, nearing room temperature superconductivity. So it's clear that this project to look for quantum coherence at high temperature in a very complex material was successful. So the other approach that was focusing on averaged electronic structure and long-range homogeneous materials completely failed. And I met Alex Muller in Italy, in Pisa, in April '87. Where we presented the results that using a local probe, X-ray absorption near edge spectra, that the holes were not copper-3 plus, but was copper-2 plus ligand-hole, but it was even more complex than copper-3 plus. It was a mixed valence between copper and oxygen with the two electronic components. This was completely unknown for a solid-state community. And however, Alex Muller understood very well the situation, and we became very good friends. So there were not 3D copper-3 plus 3D8, but it was 3D9 ligand-hole, and 3D9 ligand-hole is mixed with lattice stability, pseudo-Ian-Teller effect. Here is a picture that we took in Zurich with RICMASS, that was a very outstanding scientist in the field of bipolar and BCS condensation, Annette Guzman-Ude, Ugo Keller, Alex Mueller, and myself, and we were discussing lattice stability. Lattice stability was also for Alex an essential field. In fact, lattice stability determines the pseudo-Jahn-Teller effect that makes instability between a rhombic and a square. So there is not only electronic instability, but also lattice instability. And you have a coexistence of mixed valence, so you have a system of coherent charge moving in the undistorted lattice and distorted lattice. Using local probes like the one that Alex understood, but this was a new method using synchrotron radiation, X-rays see the local state, don't see the wave function, the wave function with plane wave that was used in the BCS theory. X-ray absorption see instantaneous configuration, and the instantaneous configuration instantons are fundamental in quantum mechanics, but was forgotten in solid-state physics. So we had the same language and became very good friends. And in early 1990, we discovered that these perovskites fluctuates between nanoscale patterns. So it was a nanoscale phase separation with a period of 2.4 nanometers and distorted lattice of 8 nanometer and distorted lattice of 16 nanometer. So our stripes had nothing to do with Frank-Wadden spin charge acceleration, but it's really due to lattice instabilities and lattice stripes. We discussed the story, all the story is in perovskite mystery in the fluctuation with the different lattice distortions. So we have a competition of local orthorhombic and tetragonal lattice, and this is an experiment that was published in November 30 years ago, in '93, and it's titled Lattice in Quantum Confinement. So where you have real stripes, lattice stripes, nothing to do with spin charge stripes, that was later, came proposed later, but there is real lattice structures. After lanthanum, we studied bismuth. Bismuth is another clear evidence of a superlattice of nanoscale stripes with period of 2.6 nanometer. 30 years ago, in 15 November, we applied for a patent. The patent was given with period in '93 and expired after 20 years in 2013. It was what is the trick of the patent? The patent is that you can create real lattice, real materials, not charge spin orbital fluctuation, but really quantum materials made of quantum wells, quantum wires, quantum dot, and quantum layers. This heretic paradigm for ITC mechanism was followed by a small group of scientists that all were good friends of Alex Mueller, and they were focusing on nanoscale phase separation, heterostructure at atomic limit, and quantum well at nanoscale. The material design of 1D periodic potential gives a flat band and one direction, the direction of the stripes, and a zip band in the other direction. So we have a very particular energy dispersion that is not like the BCS single band, isotropic band, but it's quite anisotropic with a Fano singularity in one direction and the free particle in another direction. When we are in this kind of electronic structure, I was students of Ugo Fano, and Ugo Fano was proposed in 1935 and then in 1961. The paper in physical review of Fano in 1961 now got 12,000 citations. Again, it's BCS that is 15,000, but the rate of increase of citation of the Fano paper is bigger than the BCS citation rate. So the idea of the effect of Fano is that you have two electronic components like an S wave and two quantum wells, K and L, H and P, and then you have a superconductivity that is fundamentally described by two components with a large Fermi surface and a small Fermi surface. And in this case, you have a resonance. And the theory was developed by Andrea Perali with Valletta and myself, and it is published in '96. If you introduce this quantum mechanics that was well known by Alex Muller, then you get a TC of 170 Kelvin, 190 Kelvin, with the multi-gap superconductivity. So this was predicted in '96, it's fully predicted theoretically in this paper, and in the patent in '93. What is the problem? The problem is that, so the idea of Fano was formed by Kondo in 1962, and by Anderson in 1960, same. It's called the Anderson impurity model. And Kondo is the Kondo wave function. So the Kondo wave function, or is always Fano, is a product of two many-body wave functions. One is product of one set of particles and one the other set of particles. So you have two components with two different symmetries. They cannot hybridize, and they are completely two different particles, like a neutron and protons in nuclei. What is a trick of quantum mechanics? Trick of quantum mechanics came from either London and Heidelberg and Majorana, and started to work physics. You have the exchange interaction of four particles. In this exchange interaction of four particles, you have overlap of two pairs in one band and the other band. And then everything is controlled by geometry and quantum mechanics. This kind of science is completely opposite to the Anderson valence bond to strong fluctuations. So all the mainstream of ITC superconductivity for these 30 years was completely odd with our approach. The Fano-Rashba resonance that we proposed in '96 was used by Regal in the fermionic ultra gas in 2003, and they got the Nobel Prize. But what is the trick? The trick in order to manipulate metals is to make references with the Lifshitz transition. Here you can see Lifshitz picture. I met Lifshitz in '79 in Moscow, and he was a very nice guy. He was very always smiling and he was like Fano. Fano also was always making jokes and enjoying the fascinating physics. Lifshitz proposed that there is a quantum phase transition in solids. This quantum phase transition is a metal-metal transition from a single Fermi surface to two Fermi surfaces. So you can see on the right you have two Fermi surfaces, so particle 1 and particle 2, and then you start with the particle 1, and then you have a very small Fermi surface that grows. This was called the 2.5 Fermi, 2.5 transition, because it was using an approach of non-interacting electrons. It's pure Fermi gas. But these are not Fermi gas, there is a strong electron-phonon interaction, so you have the phase separation, the phase separation that is become first order phase transition with phase separation. This was clarified by Kugel, and we made several papers together showing that the 2.5 Lifshitz transition become first order phase transition with phase separation. The physics of superconductivity in this scenario that is, I repeat, is completely different from standard scenario. I mean, resonance valence bond, TJ model, spin fluctuation. All these proposed models for trying and predicting IT superconductivity failed. And this is based on the strong electron-phonon coupling, but anomalous, because the electron-phonon coupling is strong only in the small Fermi surface. It's not homogeneous like in the Michelson theory. So the gaps and the superconductivity can be obtained easily by Bogoliubov framework. Only Bogoliubov framework with multi-gap and a single TC, but many multi-gaps is a well-founded quantum mechanics framework to understand all the physics. I've been very happy to have met in my life Alex Muller, Andrea Perali, Antonio Valletta. They all understand very well the simple and fundamental aspect of science in this field. We calculated, we developed a computer code that now is very sophisticated, and you can predict from the lattice geometry, quantum geometry, you can predict ITC and to design new materials for ITC superconductivity. So the last advance we did in this field was to introduce to replace the Dirac wave functions. In fact, the Schrödinger wave function the electrons have no spin, so it's very tricky to use the Schrödinger wave function to describe superconductivity, because in the Schrödinger the wave function the electrons have no spin, so they are bosons. On the contrary, all the superconductivity for electrons in metals is determined by the spin of the electron, so you need the Dirac equation. The non-diagonal term, the coupling matrix, multi-gap show very complex, and we made a very strong effort in 3-4 years to develop a quantum computer code that calculates exactly for the quantum geometry. Given a quantum geometry, to have the electronic structure and the superconductivity. With spin orbit, you have different helicity and different symmetries, and it's becoming fascinating. It's been published now in 3 papers in Journal of Applied Physics, and Physical Review B. So the lesson of Fano was published in Physical Review or in normal journal, not in Nature and PRL, that are not real, that are affected by fashion. So the fundamental point here is that the ITC superconductivity is given by a shape resonance between a condensate in the back BCS regime and a condensate in the BCS. So you have 2 condensates, one in the back BCS regime and one in the BCS regime, 3 particles. And the exchange interaction between the 2 components give ITC superconducting, and it's called by risonanza di forma by Majorana, it's called the shape resonance in English. The physics is a physics of 2 gaps, one in the back BCS crossover and one in the okay. What happened here is that the superconductivity is not the ITC don't appear everywhere. It's a resonance superconductivity. So you need to tune the electron-phonon coupling, the exchange interaction, the lattice geometry, quantum geometry, and using the geometry. So what Alex Muller discovered was that the perovskites are very subtle materials. They can get quantum geometries by changing chemistry. So, for example, electron-doped cuprates is a superlattice of quantum wells. The MGB2 was predicted by us to be superconductor, a superlattice of quantum wells, and it was discovered in 2001. Into 28 years after the patent, it was not considered to be BCS superconductor, it was considered to be not superconductor. So intercalated graphite, iron-based superconductor, all nanoscale heterostructure. So we have the fundamental quantum geometry, the superlattice of quantum wells, is the most simple one. And in this superlattice of quantum wells, you have Lipschitz transition with the two quite different Fermi surface. One is a larger cylindrical, and the one becomes from sphere to a critical point to a curvated cylinder. So in this geometry, you can control the interface electric field, and this uses spin-orbit coupling. Spin-orbit coupling in the Rashba Gorkov approach produces two Fermi surfaces. But this is not the important point, because in this case you have two larger Fermi surfaces. The important case to get shape resonance and enhanced superconductivity is to go here, to go in the bottom where you have complex geometry. But in this, when you go to this energy range, the spin-orbit coupling becomes of the order of Fermi energy, and then all the BCS standard approximation disappear. I want to say that we shared with Alex Mueller the idea that you cannot make a stupid approximation in quantum mechanics, like assuming that the wave function of the electron is infinite, because this is not real materials. These are approximations, and in this approximation is not described in the quantum mechanics, it becomes a quasi-classical theory. So you have to go to nanoscale, to nano device to understand what is going on. So you can find all the details of the role of superconductivity at the bottom of the edge in the spin-orbit coupling systems in our paper in Physical Review B with Mazziotti, the student that worked with us, and made a fantastic work for many years. So we have a very complex situation with one band and two band, and you have anisotropy. And then you can control the spin-orbit coupling by fundamental Dirac equations, and you get a variation of the density of states, but it's not the density of states at the critical point. The critical point in the sound understanding science is in the quantum critical points due to the Fermi stability. So you can see how beautiful is the different. These are two large Fermi surfaces as you move your lattice, and you have a spin-orbit coupling with fantastic quantum geometries. So the fantastic quantum geometry with different helicity are the key to understand and predict, because you can calculate everything in detail and predict the materials what they will do. I don't go to all the details of the theory you can find in Physical Review. But the essential point is that these are not in the PCS theory, are the exchange term. The exchange term can be only calculated with the nanoscale exact overlap of the wave function. And this is what exactly the approach that Pauli, that Eder London, Majorana, Heisenberg was considering quantum mechanics. The optimal condition for amplification of TC can be derived by all these calculations. These are in Physical Review B21. And you can see how different is the topology of the Fermi surface for non-spin-orbit coupling and spin-orbit coupling. And you can see that this is without spin-orbit and this with spin-orbit. The band edge is very sophisticated and beautiful. And the gaps, the superconducting gaps are stronger in the yellow region and very weak in black region. In the black region, the resistance is in the very weak coupling, like coupling 0,1 in BCS, while in the red coupling is in the strong coupling, like 0,3, 0,4. So Okay, so you have a resonance, you can calculate all the story, and you can find in the papers, and you find what you find is that you have a Lipschitz parameter that is essentially the trick is that you have the total dose, for example. It is a superlattice of quantum worlds, so without spin-orbit coupling you have a step like increased density of states, you have a 3D to differentiation, but you have one point here, this point here, where you have a singular point. So the dose is a one point is really one point singularity. You can see here this one, but don't contribute to the dose. On the contrary, this singularity contributes to the gap, and you have the TC. So TC becomes very large while the density of states is flat. So the reason is that you have a single singularity point that don't affect the total dose. When you do the average, you don't see nothing. On the contrary, when you use the gap of Bogoliubov, each gap in each point is dependent on the other points. So the effect of a singular point in one point in the phase space can change the DC over a large energy range. What you do with spin orbit, you change your singular point to a line. So now you increase the number of these singular points, and in this case you start to see also in the density of states a peak. And the two kinds of Lipschitz transition. The first is the appearing of a new Fermi surface, and the second one is a change, opening a neck and closing a neck in the Fermi surface. In the case of a spin-orbit coupling, the singular point becomes a line. You can see here this line. The two Mexican head, the Mexican head change, you have a line, and as this line becomes larger, the TC is larger. So when you increase the spin-orbit coupling, you increase the TC9 of the quantum critical points. So increasing the number of these quantum critical points, and the TC as an enhancer. So it's not controlled by the density of states, but it's controlled by the exchange term. The exchange term and overlapping of the four-way function is the K manipulation. And changing you have the spin-orbit coupling, and you can control it with electric field, and you can see that DC increases from up to 150 Kelvin. So with spin-orbit coupling, you can go from 40 to 150, so you can increase the superconductivity by a factor 3 or 4. So this is a new approach that implement our computer code that Perali and Valletta have developed with me, and we can manipulate the superconductivity with spin-orbit coupling and reach 200 Kelvin, like So in our scenario, the high-pressure superconductor or hydrogen materials that Hermès discovered belong to the same class of cooperates. So there is no different class of cooperates, iron-based superconductor, magnesium diborates, and in our approach, all this class of materials all belong to a unique class. Is a class dominated by Fano resonance and Lipschitz transition spin-orbit coupling, Rashba spin-orbit coupling. So the fundamental physics made by these three scientists, Alex Muller, Rashba, Fano, Lipschitz, are so fundamental that putting them all together, we can explain the quantum mechanics of ITC superconductivity. The important point is that, for example, that magnesium diboride is not a standard BCS, because there's nothing to do, because BCS is a single cap. BCS is a homogeneous electrolattice interaction. On the contrary, you have a very strong electrolattice interaction only in one point of the Fermi set. So this anomalous strong electrolattice interaction in a single spot in the K space is called G, and you can change, if you change the electron-phonon interaction in this hotspot, in the points here or here, then TC go up. And but the G is the electron-phonon interaction in the hotspot. You don't need to go to the polaronic limit like Alex wanted to see, but you remain always in the weak coupling regime. You get always 0.4 maximum, and so 0.2. So this is the anomalous unconventional electron-phonon coupling in the hotspot. And then you can get up to 250 Kelvin. So the quantum geometry that was introduced in our community, in our scientists by many scientists. It is the 20th century, and I refer to the paper of the talk of Nobel Prize of Adane, where he discussed the quantum geometry. So quantum geometry has been at the base of quantum Hall effect and anomalous quantum phase, spin orbits, all the advances fundamental. So I repeat, you can get ITC superconductivity and controlled by quantum design in superlattice or quantum effect. So you can find in the paper all the detail of discussions, and you can apply for. Let's see with the last advance we did. When you want to create a material with a very strong TC, you have two parameters essentially. One is the electron-phonon coupling in the hotspot, you see 0.004, and then you have the Lipschitz parameter, so the distance from the Lipschitz resonance. The Lipschitz transition is a quantum phase transition because it's only determined by a lattice parameter or energy. And I show you, look into the experimental data, which is the possible pathway in choosing electron-phonon coupling and the Lipschitz parameter. So because it is fundamental plot, color plot. You have TC, that is, you see 050 Kelvin, and then you have a Lipschitz parameter that is energy from the band edge divided by the dispersion in the theta direction. You can see here that you have if you go here in the maximum TC, you have a very close to lattice stability, and the materials sometimes don't grow. Always at 0.4 and 1 is the optimum point for maximum TC. But you can have different pathways. So the system, when you grow your material, sometimes you don't want to go there. So what happens in most of the known superconductors, that the pathway is this kind of pathway. So you have a very weak electron-phonon coupling, then you move, you approach the Lipschitz transition, changing doping or changing doping, and then you move here in the BCS regime, and then you go up here. Generally, the highest CC superconductors are around here. So it is prices. Okay, so including spin-on coupling, you can see that the domes change in very well way, so you get under 50 at the maximum, and the maximum TC often happen to be here at around 1.5 and 0.4. So in conclusion, we show theoretically and numerically that the atomic structure and superconducting properties of a superlattice of quantum layer with spin-orbit coupling can be predicted. The Rashba spin-orbit coupling induces unconventional Lewis transition associated with Fano singularity, negative velocity state extended on a circle whose radius increase with the Rashba spin-orbit coupling. The amplification of PC is higher where the chemical potential is tuned by chemistry or by electric field or by anything, or we see gate voltage to the conventional Lipschitz transition with the finite circuit linear quality. These results provide a roadmap to design new ITC materials, tuning the ferroelectric effect and lattice parameter, and novel quantum filtering over new barrier possibilities. An optical choice of the parameter is possible to obtain TC close to room temperature with manipulation of phenomena coupling. I thank my collaborator, Maria Di Mazzotti, Antonio Valonda, Cancio Gaetano Campi, Andrea Perali, and Sergio Guevara. Thank you for your attention.
Bianconi.
Hello?
Yes. Is there any questions? No questions.
Okay, I would like to say that in Edici we are going to have a special workshop in the beginning of August, and you can find in the superstripes.net website the information on a meeting of community that worked for many years in this field. I will be organizing with Annette Guzmanotter and Hugo Geller.
Thank you.
Thank you very much. I'm very sorry not to be there to see all my friends.
Antonio, hello.
Yeah.
Thank you for an overview, and as you know, I know most of it anyway myself as well. But you know, we always have this road to a high TC, and you said it, you can go like superlattice, and you mentioned all the core ideas. So I give you now $100 million. How do you do the lab? Do you do it by basically molecular beam epitaxy construction? So you go for artificial material, or you have a good candidate already in maybe existing materials? Which two options do you see experimentally at this very moment, please?
Okay, thank you for your comment. When we submitted the patent in '93, the technology to make our material design was very far. So we predicted a superlattice with 3 nanometer, and 3 nanometer in physical regulators paper is 2.6, and they said that the technology was at a level of 200 nanometer in '93. Now we have a technology of 3 nanometer, and technology of 3 nanometer we can realize all these materials.
Thank you.
There is no trick, so the theory is not approximation. There are no approximations. So it's a quantum fundamental quantum mechanics. There is no tricks. So it's not a resonance valence bond or tricks like TJ models. It's not a model. It's a quantum mechanics by Heisenberg, London. It's fundamental physics. So there is no tricks. So the technology was not able to make a sharp interface. With perovskites, they realize a naturally very sharp interface with LTO and LTO. Also, nature is diffuse. So you see that bismuth material have a disorder. So we started all the disorder, but you can control the disorder. And if you don't control the disorder, all the physics is there. So now we are at the age of 3 nanometer technology, so there is no problem to create artificial materials like predicted here. So we wait very few advances in few months.
Thank you for the presentation, Dr. Bianconi.
Thank you very much.